Welcome to Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be looking at our second set of notes dealing with reactions and chemical reactions. Now, the second section of Chapter 11 deals with the 5 fundamental types of reactions. So there's different patterns and different similarities in how certain types of reactions occur, and if we understand the pattern, we can use the pattern to predict, and that's in the end where we're going. But first, you need to learn to recognize the pattern, then you've got to practice the pattern, and then you put it all together. So, of our 5 fundamental reaction types, the first one we're going to look at is what's known as a synthesis reaction. Now, synthesize means to make. So in a synthesis reaction, we're taking more than one substance and combining it to make one product. So that's what a synthesis reaction looks like on the particle level. More than one reactant, only one product. So when we look at our synthesis, or what's sometimes referred to as a combination reaction, we're always going to have 2 or more substances combining to make a single product. And you'll notice as we go through our reaction types, I italics and underline kind of the key things to look for to know when you've got a certain reaction type. So this is our general formula. We've got more than one on the reactant side, and they're combining to make one thing on the product side. Now, as an actual chemical reaction, it might look like this. 2 potassium atoms combine with 1 chloride molecule to make 2 formula units of potassium chloride. But notice we're only making one kind of product. So it really has only one product substance on the product side. So 2 or more things combining to make a single product, that's got to be synthesis. Now in this case, we have 2 compounds combining to make a compound. While it's a little bit more complex to maybe know the chemistry, because 2 elements, all you can do with 2 elements is put them together. 2 compounds, there may be multiple things they could do. So while the chemistry here is a little more complex, you still see you're making just one product. That's got to be a synthesis or combination reaction. Now, next type we're going to look at is the decombustion reaction. I'm sorry, decomposition reaction. Decomposition is exactly opposite of synthesis. Instead of making one product, we start with one product and it decomposes into simpler substances. So the decomposition reaction is a single reactant breaking down into simpler substances. So one reactant, more than one product. So this would be a general formula for a decomposition type reaction. So the decomposition of water, we have a water molecule, actually 2 of them, and they're breaking apart into hydrogen and oxygen gases. So one substance breaking apart into multiple substances. Now, just like last time, you can break apart into elements, and that's a simpler way to predict. If we had a binary molecule, all you're going to do is break it into its elements. That's easy to predict. You can have more complex decomposition reactions. And while you might not be able to predict this is exactly what's going to happen, I would expect you to know that this has one reactant. It's going to be a decomposition reaction. Now, our third reaction type is combustion. And more importantly, this is hydrocarbon and oxygenated hydrocarbon combustion. So we're going to end up differentiating and talking about the type of combustions we're looking at here. But in general, combustion is of very specific types of reactions that has multiple applications. So yes, we're looking at one thing occurring, but it can occur in a couple of different ways. So when we burn the wood in a match, or when an automobile is rusting, in both cases, it's actually a combustion reaction. Now, the one on the left you probably know is combustion, or you suspect it from prior knowledge, but the one on the right you might not know that's actually combustion as well. So you need to understand combustion a little bit more. First of all, combustion is when an element or compound reacts with oxygen, often producing heat and light. So you might have a single element reacting with oxygen, like the iron in the car rusting, or you might have an element or a substance, a hydrocarbon, reacting with oxygen to make CO2 and water. So we have 2 general outcomes. We're either combining an element with oxygen, and notice this is really combination or synthesis. And that's probably more important to know because that would allow us to predict what's happening. Or you end up with carbon dioxide and water vapor. So one, we have elemental combustion, and that's also a synthesis reaction, and it's more important to know it's synthesis than it's combustion. So while it's not wrong to say this is a combustion reaction, it's more useful to know this is synthesis. So really, you don't need to know that's an example of combustion because it's more important to know it's synthesis. So on the test, I won't mark it wrong if you call it combustion, but it's not a big deal if you don't remember that's also combustion. But the type of combustion you're going to see and use is what we call hydrocarbon combustion, and it's technically also oxygenated hydrocarbon. So what is a hydrocarbon? Well, it is a compound or substance containing hydrogen and oxygen. And an oxygenated hydrocarbon would be a carbon, hydrogen, and oxygen compound like sucrose or simple sugar. It's got carbon, hydrogen, and oxygen in it. So it will also combust in the presence of oxygen, and it will also make CO2 and H2O in what we call complete combustion. So oxygen reacting with a hydrocarbon or oxygenated hydrocarbon is the type of combustion that's most important for us to understand, because this is something that drives the world. So your cars, your trucks, um, you're heating your home, cooking your food, most of those things are carried out through hydrocarbon combustion. So incomplete hydrocarbon combustion. So we're rarely going to say that word, but that word complete is important. And when we do the combustion lab, we're going to get more into complete versus incomplete. But for what we're predicting and talking about, we're always talking about complete hydrocarbon combustion. Your products are always going to be CO2 and H2O. So remember, hydrocarbons and oxygenated hydrocarbons in the presence of oxygen will always produce in complete combustion CO2 and H2O. So we have octane, C8H18 is octane, should sound familiar. That's one of the major components in gasoline, reacting with a bunch of oxygen to make a bunch of CO2 and a bunch of water. So the other product in this reaction, whole bunch of energy. And that's really what we harness when we combust octane, is we use it to end up moving our cars. So we try and harness a portion of that energy that gets created here to do some useful work. But what we have is a hydrocarbon and oxygen. This is hydrocarbon combustion. And you can just call it combustion. That's perfectly fine because it's a substance reacting with oxygen. And remember, when the substance A is an element, it's typically better to know its synthesis. And if it's a hydrocarbon, you got to know it's hydrocarbon combustion. Now, at this point, I wanted you to watch a short movie. It's short, but it talks about the process of combustion. And one thing to remember about combustion is there's often a misconception. Oxygen in a combustion reaction only supports the combustion. It's not the fuel itself, it doesn't burn. So when you're thinking something's burning in a combustion reaction, that's the fuel that you're talking about, not the oxygen. So remember, oxygen supports combustion, but it is not itself combusted. But yes, it's definitely incredibly important for the process. Now, the next one we're going to look at, the fourth of our five, is what's called the single replacement. And it's a very descriptive set of words for what we're going to describe here. A good example of a single replacement reaction is we have probably copper chloride or copper nitrate. So it's copper compound dissolved in water on the left, and we put an iron nail in there and let it sit. And over time, the bluish color in the liquid starts to disappear, and you see a whole bunch of this reddish brown solid appearing on the nail. So obviously we've got some definite chemical changes occurring here. Well, what's actually happening is what's called a single replacement. And the reason it's called that is because we have one replacement occurring. So a single replacement reaction is when atoms of an element replace the atoms of a second element in a compound. So basically we have an element in a compound, and that element is replacing a like element in the compound it's reacting with. Now, it only occurs if the elemental atoms are more reactive. And there's this thing called the activity series on page 361 in your book. We'll talk about what an activity series is and how we use it to answer this question. So if it is more reactive, higher on our activity series list, then the atoms that it's attempting to replace, will the reaction occurs. So we really need to look deeper at this. We don't just say, like with the others, this is automatically going to happen. Because when we give a certain element with a certain compound, it might be a no reaction. Nothing might occur. We have to look at the activity series to see if something occurs. So this would be the general form. We have an elemental substance A, and it's attempting to replace a like element in the substance. So if it was a metal, metals are always at the beginning. So if A was a metal, it would attempt to replace the metal in the compound, which would be represented by substance B, or element B here in the compound on the reactant side. Now, if it was a non-metal, that would be like the second one. So X, Y, similar variables here. So if X is attempting to replace Y, then it's a non-metal attempting to replace the non-metal in a ionic compound. So that's really the key, is attempting to replace. So both of these are an element of compound making an element of compound. That's kind of our dead giveaway at single replacement. But you might not actually have a reaction occurring here. And if you use the activity series and you're provided with one on the test, you can determine whether the reaction occurs or not. And the last type is double replacement. So remember, single replacement, element of compound, make an element compound, might not occur. And we're going to look at that more closely tomorrow when we actually get into predicting. Here you're looking at a reaction that has occurred. And the last one is the double replacement. Before, we only had one replacement. A replaced B, X replaced Y, that was it. The thing that got kicked out didn't go back and replace anything else. But that's what happens in a double replacement. And you've seen double replacements. Back in the ionic compound chapter, when we did the ion lab and you mixed clear colorless solutions together and you got precipitates of different colors, solid forming out of those liquids, that's actually an example of a double replacement reaction. We just didn't call it that back then. Now, in a double replacement, you have an exchange of two like things. Now, we're always talking about aqueous, so water soluble and dissolved in water ionic compounds. That's always going to be a double replacement. So if you see two aqueous compounds on the left, good hint that this thing is double replacement. So if we look at those two aqueous ionic compounds and we notice it appears that the cations traded places, then that's our double replacement. So double replacement is really the only situation where we had two compounds making two compounds. So that's a dead giveaway. We got a double replacement. And if you look closely, you can see what really happened was A and B traded places. A is now with Y and B is now with X. So it's not one replacement, it's two replacements. So A and B were trading places here. So fundamentally, that's what happens. Two replacements, double replacement. Now, I mentioned a second ago, two compounds making two compounds, and notice the two compounds on the left were water soluble. They were aqueous. That's your dead giveaway. If you see two aqueous things on the left, it's going to be attempting a double replacement. It's going to, I should say, it's going to be a double replacement. We don't get into double replacements that don't occur. That's a higher level of chemistry than we're going to see. Now, at this point, to wrap up these ideas, I want you to finish the notes by watching the reaction type movie, because it goes through and show you real examples of them and reminds you of the four key types. So that ends our second set of notes from chapter 11.